Okay, so in this scenario, everybody hates Mars apparently and want to blow the planet up. So we're gonna try to hack NASA for logical reasons. So we're gonna start off by scanning the ports. There we go. So they have an FTP at port 21 and a open socket at 1234. So let's try to brute force the FTP. So it's trying a bunch of passwords because it's a dictionary attack. And there we go. So the login is administrator and the password is why hate Mars. So let's try to connect. I don't want to waste much time here. This is just to show you how to acquire the files that we're going to reverse. Because this talk is going to be about reverse engineering in a security sense. Okay, so now we're going to analyze the file that we downloaded from NASA. We open it up in Ollie Debugger, that is a debugger, and we can see everything the file does. So we're going to start the program here, and I've already commented the code and set some breakpoints, because this process usually takes hours, and we only get 15 minutes, so I am going to speak very fast sometimes. But it's not really my fault. So we jump to the first function that I have set a breakpoint on. This is the first not boring function you see here. We just jump past these ones. So if we step into this function, we come down here and we see what it does. Here we have a memset function. This is Ollie Debugger who recognized some functions from the Windows API, Windows Win32 API, that is. And we're gonna check what they do. We step further down and we have create file A. Create file A doesn't necessarily create a file. It can open existing files. And we see that here, the third parameter, it wants to open an existing file. Therefore, it does not create a file. And the name is license.dat. Okay, so we know that the program wants to open a file called license.dat. Then the program wants to read the file and put the content into a buffer. It can read up to 600 bytes. And then it compares the size of the buffer. So the size of the file, it compares it to 16. And how do we know it's 16? Well, 0f in hexadecimal is 16 in decimal. So it compares the buffer size with 16, and then it jumps. If our buffer is over 16, it will jump, and it will jump to here. And if it's below 16, it will just continue and exit. So we need to have a file called license.dat, and that file needs to be over 16 bytes. So I've set a breakpoint here. We need to close this program. We need to close the program, and we need to create a file called license.dat. So we make this file larger than 16 bytes. We save it. We open up Ollie Debugger. We run the program again. And this time we hope that it can read the file. So we jump to our breakpoint, and just before it compares the files, and it jumps. Our file buffer was larger than 16, so we skipped exit process. That's cool. So we step even further down and we see a loop. How do we know it's a loop? Well, Ollie Debugger pretty much painted it out for us, and we can see it here. And we see that this upwards arrow, this jump, is upward to here. And the loop takes a string length, so it loops through a string, probably the content of our buffer, our license file. It needs to check that the license is right. So we go down, 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 down. Okay, so it takes the first character. We see the character here. It's 41, but in ASCII it's A. And it compares it with X. How do we know it's X? Well, it compares it with 58, and 58 in hexadecimal is 88 in decimal, and 88 in decimal is the character big X. So we step even further down, it goes through the whole string, it increases the counters, increases more counters, and it's gonna jump up to the top because it's gonna read through the whole string, and we don't want to wait for this. So we set a breakpoint and we just let the program run. So now we're out of the loop. It compares something with 6. It probably compares the X counter with 6, because that's pretty much the purpose of the loop, to count the X's. And if the count of X's is 6, we are going to jump over the exit process, but we don't have any X's, so therefore we set a breakpoint, we close the program again, and we have to edit our file. We need 6 X's. So 1, 2, 3, 4, 5, 6, and remember the file buffer needs to be over 16 bytes. So we just fill it up. Now we start Ollie Debugger again, and we go to our breakpoints. Look now. Now the zeros change to a 6 because we have 6 X's, and we take the jump hopefully down here, and bam. So we crack the license file, and that's pretty gangster. Not that gangster. That gangster. So this is the function where we last stopped. This is the function after the license function, and we already have a working license, so let's continue here. We go into the function and we see WSA startup, so it's probably going to be sockets, and we have an IP, so it's going to be sockets. We have H to NS, and we get a value of 4D2 in hexadecimal, and that's 1, 2, 3, 4 in decimal. So it's a port function that translates the port to bytecode, and 1, 2, 3, 4 is the port that was open when we scanned NASA, so this is the same program. We get a socket with IP protocol TCP, we get a bind, so we're gonna have a listen, there's the listen, and an accept. So now Ollie wants a connection, and we can't step anymore in this program unless we have a connection. So I've written a Python script, and this creates a socket. It connects to an IP and a port, and then it starts to listen in a while loop. So we have to run this program, run the script, and Ollie starts shouting that it wants something. So we can step through now. We get a send, so we get something back from the program. Let's see what. We get a 4-byte message that says auth, so it's probably an authorization. Okay, so the IP was hard written in the program, so maybe there's something more. So we're gonna search for all referenced text strings. we see the IP here, and this is things they have written in the program code. And we see NASA admin space is cool. That seems to be a login. So we can't step through anymore because the program wants some input. So let's send it NASA admin space is cool. And Ollie starts shouting again. Hey, I got something. So we step through even more, and it copies the string. And we see here, it copies what we wrote into a destination. What if this destination has a buffer smaller than what we wrote? We are going to look at that later. But just think about it. So we're stepping through the program and we see a text string, and this is what we found when we searched for referenced strings. It puts it in a buffer and probably will compare what we wrote with this. Because when we go down, we see ex equals 0 and jump if not 0, so we are going to jump. But we don't want to jump, we want to see these messages and the receipt. So let's fake it. So we set the 0 flag and then we don't jump. So we go down, 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 and we get the message. We get 17 bytes message, apparently. So if we look at our command program again, we see rover command. Okay, so we can send commands to the Mars rover, the Curiosity rover. Like we need to go first, so we have data 4 was equal to auth, right? That was the first message we got. Then we need to send NASA admin space is cool, right? So then we need to send data and continue, right? But then we got rover command. So what if the first message was rover? And say we send the buffer was pretty small, and we want to write 1,000 A's times 1,000. What is going to happen with the program then? Okay, we're going to talk about string copy. What it does is it takes the source and copies. Okay, so what happens when we write a buffer that big? So we see the stack. We can see the stack over here and the addresses. And here is the instructional pointer. When we send a too big buffer that the program can't handle, really, it's just gonna overwrite everything. And we wrote 1,000 A's, and the A's have the character 41, the decimal number of 41. So if we look at a fake stack that I just written, it's gonna be all 41, 41, 41, and the instructional pointer to the next instruction will be 41, 41, 41, and that's the program crashes. It's made to crash if you test it like that. It's called fuzzing to test programs. So what if we log in, and when we get the rover command, we just write some chunk data to overwrite the return with no operations. So when the return should come, it just comes no operations. And then we write our own payload. And this is a payload. So we send the no operations and the junk and the payload and the and no operations. And what this payload does, it instead of returning as it should be, because the return address value has no operation, so it won't return. It will just continue to read our code. Okay, so the payload opened the port 4444 on the NASA server, so we're just going to connect to it with netcat. It's a great tool that can everything and anything. So when we connect, you see that close secure over the it's NASA's. So we're just going to export files. And see commands.txt. That's what we wanted. So let's. So we see the commands there. Start rover. This is the Curiosity rover on Mars. See here underlined start, stop rover. See here stop, blow up Mars. See here blow up Mars. So, and that's the main goal of this scenario. So let's blow up Mars. So we need to make the script for it. So we don't want to send 10,000 days anymore. Let's just send it here, blow up Mars. Okay. execute the script and bye bye Mars.